So in this video, we're going to talk about exploring data in SPSS. And in particular, we're going to be thinking also about testing differences between groups based on the mean, such as an Anova. So we'll talk about things like histogram, tests of normality, um, and then looking at Anova results. And we're also going to talk a little bit about how to recode a variable so that SPSS can view it as a factor for the Anova. All right, let's get started. All right, so first, I'll put a link to this in the video notes, but we're going to start with looking at this data set about roller coasters, and these are data that are not necessarily real world. They were collected as part of a Roller Coaster Tycoon data set that's available for free on Kaggle. At any rate, so one question that you might be able to ask with some of this data, and I'm showing you here the variable list that's in the data set, is are there differences in average nausea level across roller coasters with different excitement ratings? This is something you could also think about how to answer this using a regression to see if, for instance, as nausea rating or level goes up, does that also mean that the level of excitement is going up with it? Is there a correlation between the two? But in this case, we're interested in this piece in which we have this excitement rating variable, which is nominal. And right now it's a string variable. So that's why we're going to have to change this, because if we try to run an Anova on this with the string, it's not going to recognize it in the right format to separate it out as a grouping variable or as a factor. Those have to be numeric, but set to be nominal, if that makes sense. Okay, we'll get into that in a minute. So the first thing to do if you're just trying to explore the data is to start by going to Analyze and Descriptive Statistics and Explore. I really like this option. And it allows us to take the nausea variable. You'll notice it has a ruler next to it, meaning it's a continuous variable. It has ratings from about 0 to about 10. So if we think about that being different across these excitement rating variable, and you can see the little nominal symbol here, meaning that it is distinct groups. And that's what we want to use this factor list for, is to say these are the groups that we want to compare against each other. So we're going to separate the nausea variable out by these groups, which are listed as low, medium, high, and very high. So take a look at these other options as well. You have statistics. I'm not going to put this in here, but you could look at outliers or percentiles, so I'll show you what's there. Perhaps the most important thing here is we don't really want to look at a stem and leaf. A histogram is much more helpful for us. And it could be helpful to look at normality plots with tests because we are looking forward to running an Anova with this, which does have a requirement that data are normally distributed. Click continue. And make sure that we're displaying both statistics and plots here. So if we click OK on this, give it a second to run. Do, 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 do. There we go. It's starting to pop up. All right. Don't worry about these warnings up here. This is saying there are words that are longer than 8 characters. Okay, we're not concerned about that at the moment. For now, let's look at this case processing summary, which tells us how many of each variable are in the data set. So looking at high, there are 116 roller coasters that were listed with the high excitement rating, but Look at the rest though. We only have 2 for low, 12 for medium, 12 for very high. That could present some issues, especially the 2, but also with regards to another type of assumption, which is homogeneity of variance for Anova, meaning that the variances are the same. So if you have a smaller sample, like 12 or 2, there is less opportunity for those variances to sort of level out. So the 116, there's a whole lot more data there to establish a variance with. So you're going to have perhaps a completely different range even of nausea ratings within high that are even possible than especially with low. So that is something that we'll have to take into consideration at a later point. I'm not going to talk about the homogeneity of variances piece much today. Okay. So descriptives can look at the mean nausea level for the high excitement roller coasters. Have a mean of 4.3, a median of 4.2. So those are pretty close to one another, meaning that it's likely that things are going to be more normally distributed. Standard deviation of 1.3. We can see the range, the minimum from 2 to almost 10, a range of 7.7. Skewness and kurtosis values, generally we want those between plus or minus 2, which they are. So this looks like it's probably normally distributed. If we look at low, we're not going to get very good data here. Remember, there's only 2 data points. So a mean of 2, a median of 2.1, minimum, maximum just goes from 1.6 to 2.6. And it didn't even calculate skewness and kurtosis or interquartile range because there are only 2 data points. There's not enough data to actually calculate those with. And then the medium group, a mean of 3.6, a standard deviation of 1.1, range of 4.7, interquartile range about 1, and skewness and kurtosis look okay there, and they look okay here too for the high or very high group, mean of 5, standard deviation 1.4, a range of 3.8. So the ranges are very, very different across these. And we can see that showing up in the test of normality too, that we have these skewness and kurtosis values that appear to be within range, but something isn't right. So if you see here, if we look at the Kolmogorov-Smirnov test, we have significance values that are well above 0.05, and that's what we want here. Remember, it's testing. The null hypothesis is that that things are normally distributed. So if we get a statistically significant test of normality, that means that the distribution has deviated a lot from what it would be if it was normal. If it was normally distributed. So, but the Shapiro-Wilks test here for the high group is giving us a statistically significant result, and the low group, of course, we're not really able to look at that because there's only 2 data points. So it looks like probably everything is going to be pretty good. It also is giving us a possible statistical significance issue here with the very high group if we're using 0.05 as a cut score. So we need to look at these histograms to help us make more sense out of that. So we scroll down a little bit. You see the histogram for the high rating group. It does look like there's some skewness to the right, and in particular this value over here that's almost 10 is making it look like that. But even if we just look at this group, it does look like it's not very symmetric. There is a little bit of skewness to the right, a positive skew. If we look at the medium group, remember, there's only 12 data points, so that's another issue that's causing some problems here. We see that there is perhaps some symmetry. It doesn't look too bad to me, to be honest, but there's not very much data to go on. And for the very high group, it looks like it's probably a little bit skewed to the right because of this bar here, but there's so few data points in each of these bars that this one is even more difficult than the medium group to tell. So there are some potential normality issues to note, and the QQ plots can help us also examine this. So if you don't remember, what we're looking for here is that the points stay relatively close to a straight line following this black line here. If it was perfectly normal, every single one of these data points would be on that black line. So basically what it's doing here is saying, if it was normal, that's the y-axis here. That's the point where we know it should be if it was normal, but the x-axis is what we actually see in the data, what the points actually are. So you can see here a little trailing off. And this is that point on the very far right that we noticed. So what this is telling us is that the data is shifted a little bit too far to the left. And if you remember from the histogram of this high rating group, there was a concentration of data points. Oops, that's not keeping up with my scrolling here. So this high rating group, if you look on the left side here, there's a little bit more data here than there should be. This center right here, or the sort of mode where it peaks, is a little bit farther to the left than where it should be. If it was normal, that would be further this direction, maybe over here somewhere, so that it would be symmetric. And so that's why we see in this QQ plot some points on the left side here that are falling below that line. That's because there is too much data on the left side. And we see the data trailing off over here because it's skewed to the right. So that point is way off of where it should be. It should be much closer to the rest of the data. Okay. If we keep going a little bit, so this is the one with just the 2 data points, so there's not much to look at there. If we look at the medium group, it actually doesn't look that bad. Things sort of flow back and forth across this line, which is okay. Nothing looks too far off. Maybe this one's a little bit far away, but nothing horrible, kind of like what we were looking at. And this one is a little bit more difficult to tell that it's actually a straight line. And a lot of this, again, is because there's only 12 data points. So keep that in mind. But just, I think getting used to looking at these plots is important. And then if we look at the box plots, this is going to be helpful for us in thinking about the Anova test that we're thinking about running and answering our question. So if we look at the box plots across here, obviously the low group, there's only 2 data points there, but much lower nausea rating in the low excitement roller coasters. And also this group, medium group, is quite lower. And the very high group is different a little bit too than the high group, but not by as much. However, something else to think about is the variance across these groups. So if we look at the medium group, there is a pretty small range where most of the data is, and notice there's a couple of outliers here, but the majority of the data is within a pretty small range compared to the high group. And remember, the high group had 116 roller coasters in it. And then the very high group also has kind of a smaller range than that. So we may have an issue with the assumption of homogeneity of variances with that. So before we can actually run this test, though, I'll show you why it's not going to work. So remember, we're comparing means across groups. That's what an Anova does. So we go to compare means, and then a one-way Anova. And when you click on that, you'll notice here that there is no option in here to select the excitement rating group. We could pick the custom design group because that's just a 1 and a 0. That's why it's showing up. But the excitement rating variable is has text in it rather than number values that indicate groups. And unfortunately, there is no way to make SPSS recognize that without actually transforming the variable. So we have to go to transform, and we'll choose recode into different variables. And I suggest always doing this because you don't want to run the risk of doing something wrong and then you can't get back the original data, or you can't check it to make sure that you coded things correctly. So this actually is a pretty straightforward thing to do. Um, so we're going to pick the excitement rating variable as the input variable. And the output variable over here in this box, we need to pick a name for this. And the easiest thing to do is just to call it excitement rating 2 or something. And then click this change button, because if you notice there's a question mark here. So if we select change, it will put it there, meaning we're going to take the excitement rating variable, do something to it, and save it as excitement rating 2. And the something that we're going to do to it, we get by clicking on this old and new values button. So click on that. The first thing you always want to do is tell it that anything that is system or user missing, that is indicating that there's a missing value, you want to retain those. So under the old value box, click if the old value says it's missing, then also make sure that it's missing in the new value and click add. So we can see if it's missing over here, it's going to still be missing in the new variable that we're creating. Okay, so the old value, remember it was low, medium, high, and very high as the words, and you can see that down here. So old value, if the old value says low, then we're going to translate that into a 1. So we see after we click add low arrow 1. So that looks correct. Then can put in medium is going to be a 2 and click add. High is going to be a 3 and then click add. And then very high. And you'll notice down here, it looks like it didn't include the H. The H is actually there in the data set if you look at it. It just truncated it because it will only print strings that have 8 characters or less for some reason in SPSS programming. So it actually does have the H at the end of it if you look at the actual data. And we're going to make very high be a 4 and click add. So check through here, make sure it looks right. Low is a 1, medium is a 2, high is a 3, very high is a 4. Missing is going to stay as missing. So everything looks like it's correct. Click continue. Click OK. And in the output window, you'll see that it says to do that. Low equals 1, medium equals 2. And then if we go back to the actual data, you should see that has been added at the end. Excitement rating 2. It is a numeric type. And on the right, make sure that it recognizes it as being nominal, that it didn't change it to a scale variable. We want it to be nominal so that these values are recognized as groups. Okay, so then if we go back here, and then we can go to analyze, compare means, one-way Anova, and if you scroll to the bottom, you'll see our new variable there listed. And we want this to be the factor. In SPSS, when we think of the word factor, we're thinking of grouping variable. That is what the factor is telling us about. And of course, we're comparing nausea levels across these excitement ratings. So we want nausea as the continuous variable in our dependent list. And we could go ahead and go in here and run some post hoc just in case it actually ends up being that way. We do want to check if equal variances are assumed. If you want to look at that assumption, we will check that in a minute. So if the equal variances are assumed, I recommend using Tukey. If equal variances are not assumed, which we won't know till we actually see it, but we have some suspicions that the variances are not assumed. We can't assume they're the same. I'm going to click the Dunnits. T3, continue. We can look under options. We could go ahead and grab descriptives. We want the homogeneity of variance test. Click continue. And let's click OK. And what that's going to do is a pairwise comparison across all the different groups. And remember, we have some issues with the groups anyway because that low group is so small. So if we were doing this in reality, we'd probably want to pool some of these together to make larger group sizes. So you can see here, 1, that's the low group. There was 2. 2 is the medium sized group. There's 12. 3 is the high group. There was 116. And then 4 is the very high group. There was 12. So you can see that. We can look across the means and see that there's quite a difference across the means. And more importantly, maybe, is the standard deviations are quite different because of this group with only 2 in it. Other than that, the standard deviations look pretty similar. But if we look at the homogeneity of variances section, which standard deviation is the square of the variance. So homogeneity of variance, one way to get a quick picture of that is to look at the standard deviations. And we're looking at the row that says based on mean. This is the Levene's test. We see the p-value of 0.593, and the test of homogeneity of variances says, the null hypothesis says variances are equal. So we're not rejecting that, meaning they're similar enough that we don't have to worry about it. So when we look at our post hoc test in a minute, we can look at where it says variances are equal variances are assumed. And we picked the Tukey's as the pairwise comparison. So then we look at the Anova table. We can see between groups, we have an F statistic of 4.146. That's pretty high. And a statistical significance, a p-value of 0.008-ish. It's rounding it to that. So in this case, we would be looking at this thinking, okay, across all the excitement ratings, nausea appears to be different. The mean nausea value for all the roller coasters in those groups is different somewhere. There's at least a pair of those roller coasters where things differ from one another. It's a big bird's eye level view across the groups. It doesn't tell us which pair of groups there is a difference between. Are there differences between all of them, between some of them? That's why we need the post hoc tests, which run pairwise comparisons. So if you look at Tukey, remember, we're not going to look at the Dunnett because that was for if we couldn't assume variances were equal. But the homogeneity of variances test tells us we can. So Tukey says if we compare 1, which is the low group, to 2, which is the medium excitement group, we get a p-value of 0.471. So that's telling us there's not a difference. Although group 1 may not be the best one to be comparing to because there was only 2 people or 2 roller coasters in there anyway. If we look at the other groups comparing 1 to 3 and 1 to 4, we see close to something different here, or if we were using 0.1 as a cutoff instead of 0.05, we can make a claim that there was a difference. And we see a statistically significant difference between low and very high excitement, with the very high group having more nausea in this case. And right here you can see that the mean difference, so it's subtracting the nausea rating for 1 minus the nausea rating for 4, which gives a negative value. So the nausea rating for 4 is higher by almost 3. If we're comparing 2, we already compared 2 and 1, so 2 to 3 and 2 to 4, we only see a difference between the medium group and the very high group. 0.047 is the p-value for comparing 2 to 4. And then the only comparison we haven't done yet is comparing 3 to 4, which is not statistically significant. So really the only things that matter are comparing low and medium to high. And so if we look at the high group here, a high compared to low and medium are statistically significant. So very high has statistically significant higher nausea values than the low and the medium, but there's not differences anywhere else. That's it. So we can say extremely high excitement causes a lot more nausea than things that have low or medium levels of excitement. It appears that they're associated with one another, or that the differences are statistically significant. Okay. All right, and that's it for this video. And let me know what questions you might have. Thanks.